So in our previous lesson, we saw how that if we had a current running through a wire, and if this current running through a wire was in the presence of an external magnetic field, just as we have in this diagram over here, we saw how that can actually induce the wire itself to move in a particular direction. We saw how that there was actually a magnetic force being thrust upon the wire itself. And in this particular case, we saw how it moved towards the left. Now, what we're going to do today is we're going to do something a little bit different. We're going to see if we can now do the reverse. So in this particular case, what if we were to take a bar magnet and move it close to or towards and away from a coil? In other words, we're going to try to do the reverse of what we did before. So if you take a look at this diagram here, you see how there's a south end of a bar magnet moving towards a coil, as you see. And in this particular case, the south end of the bar magnet is moving towards the coil. It turns out that this induces a current to flow in the coil itself. And as you can see in this diagram, the current in the coil on your side is actually flowing upwards, okay? And it completes the circuit, as you can see in the ammeter below. Now, take a look. If I were to wrap my right hand around this coil, what this actually does is that it induces a magnetic field such that the left side of the coil becomes a north, and the right side of the coil becomes a south. All right? So wait a second. If the south end of the bar magnet is being pushed towards a coil, what ends up happening is that the induced magnetic field, as shown in green, is now created so that it opposes the motion of the magnet itself. If the magnet is being pushed towards the coil, the induced magnetic field will now act to repel the bar magnet. Okay? Now, if I take a look at the next situation over here, once again, I have a south end of a bar magnet being pushed away from the coil. Okay? So the south end of the bar magnet is moving away from the coil. Take a look to see what happens in the coil itself. In this example, what happens is that current in the coil is now reversed to flow in the opposite direction. And this can be seen in the ammeter below. Now, once again, using right hand rule number 2, if I were to wrap my right hand around the coil, you will notice that in this particular example, the north end of this induced magnetic field is now on the right, and the south end occurs on the left. And if you take a look at where the bar magnet and the coil are closest, we have the north end of the induced magnetic field and the south end of the permanent magnet. These two will now act to attract each other. Okay, so once again, we are opposing the direction of the magnet itself. If you have a look, south end of the magnet is moving away from the coils. That means the coils have to have a magnetic field induced upon it that will help to attract the bar magnet. Now, I know that's a little bit confusing to understand, and to help us to understand this a little bit better, or one of the analogies I like to use is in reference to, I guess, the dating game. All right, so let me talk a little bit about this dating game using two of the better-known pop stars of the day, Justin Bieber and Selena Gomez. Let's have a look. Okay, so as you can see here, here we've got Justin Bieber here on the left, and we've got Selena Gomez here on the right. And as everyone knows, these two have a mutual attraction for each other. Justin Bieber likes Selena Gomez. Selena Gomez likes Justin Bieber. How cute they are. Okay, wonderful. So what's going to happen is this. So let's suppose that before they even met, before they even started dating, let's just say that Justin Bieber made the first move. Okay, so here's Selena Gomez on the right. She is not moving at all. And here's Justin Bieber on the left. Justin Bieber is now going to get a little bit closer to Selena Gomez. Okay? Because that's what guys do. Guys, if they like a girl, they're going to try to get closer to the girl. Now, what is Selena Gomez supposed to do? Well, the smart girl will say, Justin Bieber, I want you to back off, okay? So what she's going to do is she's going to try to repel him, okay? So she's going to try to repel on approaching Justin Bieber. So what happens? He gets repelled. Now, what's going on here is that as Justin Bieber is getting repelled, Selena Gomez has to be thinking, well, wait a second. I know he likes me. I like him. I don't want him to go too far away. I kind of want to keep him, close by. I want to keep him on a leash. So if he's getting further and further away from Selena Gomez, what she wants to do is she wants to try to attract him again. So let's try to re-attract Justin Bieber. So she will now re-attract Justin Bieber. And now he gets closer to her again. Now, as he gets closer and closer and closer to her, what do you think she should do? Once again, if you're the smart girl, you will try to repel him. Okay? So what happens when you repel Justin Bieber? Well, when you repel Justin Bieber, you get further and further away. But you don't want him to go too far away. So what should you do if he gets too far away? You try to attract him back. So now he's getting re-attracted back to Selena Gomez. But if he gets too close, and as you can see, there is another interruption from the main office. In any case, if Justin Bieber is getting too close to Selena Gomez, she should again repel. If he gets too far away, attract. Getting too close, repel. Getting too far away, attract. And so on and so forth. All right, so hopefully you guys all understand that analogy. So the question now becomes, why would that make sense? Okay, why does it make sense that if you are a bar magnet approaching a coil, why would the coil want to reverse the reaction? Why would it want to do the opposite of whatever the bar magnet is doing? And to help us understand the answer for that, what we're going to do, we're going to turn back to something that we've seen before, the law of conservation of energy. What I want you to do really quickly is I want you to focus on the screen, in particular this diagram over here that says figure 18.20. So I want you guys to focus on this diagram. Oops. Try that again. I want you to focus on this diagram over here. Okay, so let's take a look at what's going on in this diagram. So first of all, I'm going to see if I can rationalize exactly why we see what we do. Let's pretend, for example, that in this particular case, we have the north end of a bar magnet approaching the coil. Okay, and you can see that by the green arrow that's already shown. So the north end of the bar magnet is approaching the coil. Again, now think about it this way. If Justin Bieber is getting too close to Selena Gomez, what should Selena Gomez do? She should repel. Okay? Now, what normally repels a north? Well, we know for a fact that if a north is approaching, we are going to repel it with another north. Okay? So if the right side of the coil becomes a north, that means the left side of the coil should become a south. Now, let's use right hand number 2, or the right hand for coils, to see if we can wrap our right hand around the coil so that your thumb is going towards the north end of the induced magnetic field. If you wrap your right hand around the coil, you will notice that the current on your side of the coil is actually going in the direction that is shown. Okay, and this is the correct answer. This is what you would actually see. Now, let me just play devil's advocate here, and let me just see what happens if the reverse were to happen instead. So I'm going to erase all these things I've already drawn. Now, once again, take a look at the same diagram. The north end of the bar magnet is approaching the coil. So let's pretend that instead of the right side of the coil repelling the bar magnet, what would happen if it were to further attract it? Okay, so to attract the north end of a bar magnet, that means the right side of the coil should become a south, and the left side of the coil should become a north. Once again, if you use right hand rule number 2 and wrap your hand around the coil so that your thumb is pointing towards north, you would find that current is flowing in that direction. Okay? Now, this is, of course, the wrong answer. So why would I go about trying to show you the wrong answer? Let's take a look at what we're looking at. Let's take a look at what's going on here. The north end of the bar magnet is approaching the coil. If the side closest to the north end is induced to become a south, what that means is that the bar magnet is going to be further accelerated towards the coil. That means the bar magnet moves faster. If the bar magnet moves faster, guess what happens to the induced current? The induced current now becomes stronger. If the induced current becomes stronger, guess what happens to these induced magnetic fields? That means the induced magnetic fields will also get stronger. Well, wait a second. If they get stronger, guess what it does to the north end of the bar magnet? It attracts it even more and causes it to accelerate at a greater rate. Well, if the bar magnet keeps on accelerating over and over and over again, guess what happens to the current in the coil? It goes ever increasingly, or I should say infinitely, faster. If the current gets infinitely faster, guess what happens to the induced magnetic fields? They get stronger and stronger and stronger, infinitely. In other words, the bar magnet moves faster, therefore increasing its kinetic energy, and the current gets stronger as well, therefore increasing the electric potential energy. What have we just done here? We have now violated the law. What we've just done here is that we've violated the law of conservation of energy. Okay? And we know for a fact that energy cannot be created, can't be destroyed, but it can be converted to from one form to another. And that hasn't happened in this example. Okay? So for that reason, you must understand that whenever we are talking about induced magnetic fields, the polarity of the induced magnetic field must always act to oppose the motion of the bar magnet itself. So once again, if the north end of the bar magnet is approaching the coil, that means that the right side of the coil must act to oppose that north end by becoming a north and the opposite end becoming a south. If you wrap your right hand around this coil, you will notice that current can only go in that direction. Okay? Let me give you another example. If you take a look at the diagram just below there, diagram C, just in case, just to make sure that you're looking at the same diagram, I'm going to put a little circle around diagram C. In this case, take a look. I now have the north end of the bar magnet moving away from the coil. Kind of like Justin Bieber is moving away from Selena Gomez. Well, you don't want him to go too far away. You want to keep him on a leash. You want to try to reattract him. Well, what reattracts the north end of a bar magnet? Well, we all know that that's going to be a south. So that means the right side of the coil should become a south. The left side of the coil should become, or should be induced to become, a north pole. If you wrap your right hand around the coil, you should see a current that flows in that direction. Okay? So hopefully that makes some sense. And the rationale that we've just explained here to determine the direction of the induced current and the induced magnetic field, this is what we often refer to as Lenz's law.